Neutron stars are one of the most extreme and violent things in the universe. Giant atomic nuclei, only a few kilometers in diameter, but as massive as stars. And they owe their existence to the death of something majestic. Intro music. Stars exist because of a fragile balance. The mass of millions of billions of trillions of tons of hot plasma are being pulled inwards by gravity and squeeze material together with so much force that nuclei fuse. Hydrogen fuses into helium. This releases energy, which pushes against gravity and tries to escape. As long as this balance exists, stars are pretty stable. Eventually, the hydrogen will be exhausted. Medium stars, like our Sun, go through a giant phase, where they burn helium into carbon and oxygen before they eventually turn into white dwarfs. But in stars many times the mass of our Sun, things get interesting when the helium is exhausted. For a moment, the balance of pressure and radiation tips, and gravity wins, squeezing the star tighter than before. The core burns hotter and faster, while the outer layers of the star swell by hundreds of times, fusing heavier and heavier elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day. And then death. Iron is nuclear ash. It has no energy to give and cannot be fused. The fusion suddenly stops, and the balance ends. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. What happens now is awesome and scary. Particles like electrons and protons really don't want to be near each other. But the pressure of the collapsing star is so great that electrons and protons fuse into neutrons, which then get squeezed together as tightly as an atomic nuclei. An iron ball, the size of the Earth, is squeezed into a ball of pure nuclear matter, the size of a city. But not just the core. The whole star implodes, gravity pulling the outer layers in at 25% the speed of light. This implosion bounces off the iron core, producing a shock wave that explodes outwards and catapults the rest of the star into space. This is what we call a supernova explosion, and it will outshine entire galaxies. What remains of the star is now a neutron star. Its mass is around 1,000,000 times the mass of the Earth, but compressed to an object about 25 kilometers wide. It's so dense that the mass of all living humans would fit into 1 cubic centimeter of neutron star matter. That's roughly 1,000,000,000 tons in a space the size of a sugar cube. Put another way, that's Mount Everest in a cup of coffee. From the outside, a neutron star is unbelievably extreme. Its gravity is the strongest outside black holes, and if it were any denser, it would become one. Light is bent around it, meaning you can see the front and parts of the back. Their surfaces reach 1,000,000 degrees Celsius, compared to a measly 6,000 degrees for our Sun. Okay, let's look inside a neutron star. Although these giant atomic nuclei are stars in many ways, they're also like planets with solid crusts over a liquid core. The crust is extremely hard. The outermost layers are made of iron left over from the supernova, squeezed together in a crystal lattice, with a sea of electrons flowing through them. Going deeper, gravity squeezes nuclei closer together. We find fewer and fewer protons, as most merge to neutrons, until we reach the base of the crust. Here, nuclei are squeezed together so hard that they start to touch. Protons and neutrons rearrange, making long cylinders or sheets, enormous nuclei with millions of protons and neutrons shaped like spaghetti and lasagna, which physicists call nuclear pasta. Nuclear pasta is so dense that it may be the strongest material in the universe, basically unbreakable. Lumps of pasta inside a neutron star can even make mountains at most a few centimeters high, but many times as massive as the Himalayas. Eventually, beneath the pasta, we reach the core. We're not really sure what the properties of matter are when they're squeezed this hard. Protons and neutrons might dissolve into an ocean of quarks, a so-called quark-gluon plasma. Some of those quarks might turn into strange quarks, making a sort of strange matter with properties so extreme that we made a whole video about it. Or maybe they just stay protons and neutrons. No one knows for sure, and that's why we do science. That's all pretty heavy stuff, literally, so let's go back out into space. When neutron stars first collapse, they begin to spin very, very fast like a ballerina pulling her arms in. Neutron stars are celestial ballerinas, spinning many times per second. This creates pulses because their magnetic field creates a beam of radio waves, which passes every time they spin. These radio pulsars are the best-known type of neutron star. About 2,000 are known of in the Milky Way. These magnetic fields are the strongest in the universe, a quadrillion times stronger than Earth's after they're born. They're called magnetars until they calm down a little. But the absolute best kind of neutron stars are friends with other neutron stars. By radiating away energy as gravitational waves, ripples in space-time, their orbits can decay, and they can crash into and kill each other in a kilonova explosion that spews out a lot of their guts. When they do, the conditions become so extreme that, for a moment, heavy nuclei are made again. It's not fusion putting nuclei together this time, but heavy neutron-rich matter falling apart and reassembling. Only very recently, we've learned that this is probably the origin of most of the heavy elements in the universe, like gold, uranium, and platinum, and dozens more. So now two neutron stars collapse and become a black hole, dying yet again. Not only do stars have to die to create elements, they have to die twice. Over millions of years, these atoms will mix back into the galaxy, but some of them end up in a cloud, which gravity pulls together to form stars and planets, repeating the cycle. Our solar system is one example, and the remains of those neutron stars that came before us are all around us. Our entire technological modern world was built out of the elements neutron stars made in eons past, sending these atoms on a 13 billion-year journey to come together and make us and our world. And that's pretty cool. Formation of neutron stars. Neutron stars are the remnants of massive stars that have undergone supernova explosions. This occurs in stars with masses between 8 and 25 times the Sun's mass. Here's how it happens. Nuclear fusion and equilibrium. Stars shine due to nuclear fusion, where lighter elements like hydrogen are fused into heavier elements, releasing immense energy. This energy balances the inward pull of gravity, maintaining the star's stability. Collapse and supernova. When a massive star exhausts its nuclear fuel, its core can no longer support the gravitational pressure. The star collapses rapidly, and the outer layers are ejected in a supernova explosion, outshining entire galaxies for a brief period. Core collapse. In the collapsed core, the density becomes so high that electrons and protons combine to form neutrons through inverse beta decay. The result is an incredibly dense object, the neutron star. Physical characteristics. Neutron stars possess some of the most extreme physical properties in the universe. Density. A neutron star packs about 1.4 times the mass of the Sun into a sphere only about 20 to 25 kilometers, 12 to 15 miles across. A single sugar cube-sized piece of neutron star material would weigh billions of tons on Earth. Gravity. The gravitational pull at the surface of a neutron star is about 2 times 10 superscript 1 superscript 1 times stronger than Earth's gravity. This gravity is so intense that it significantly bends space-time, allowing you to see parts of the back of the star while observing the front. Temperature. Newly formed neutron stars have surface temperatures of over 1 million degrees Celsius. Over time, they cool, but due to their compactness, they remain hot for millions of years. Magnetic fields. Neutron stars have magnetic fields 1 trillion times stronger than Earth's. Some, called magnetars, possess magnetic fields so strong they can distort atomic structures and emit high-energy bursts of gamma rays and X-rays. Spin. Neutron stars can rotate extremely rapidly, hundreds of times per second. This rapid spin is a result of the conservation of angular momentum as the massive star collapses into a much smaller neutron star, akin to a figure skater pulling in their arms. Internal structure. The interior of a neutron star is an area of intense study, as it challenges our understanding of physics. Crust. The outermost layer is a thin crust made of iron nuclei and a sea of free electrons. This crust is immensely strong, far exceeding any material found on Earth. Nuclear pasta. Beneath the crust lies a region where atomic nuclei are compressed into bizarre shapes resembling spaghetti, lasagna, or gnocchi, collectively called nuclear pasta. This material is thought to be the strongest substance in the universe. Core. The core is where the mysteries multiply. It could contain neutron superfluid, a quantum fluid made entirely of neutrons. Quark-gluon plasma. If pressures are high enough, neutrons and protons could break into their constituent quarks, forming a dense soup of quarks and gluons. Exotic matter. Some models suggest the presence of strange quarks or other unknown particles. Types of neutron stars. Neutron stars exhibit various phenomena based on their characteristics. Pulsars. These are rapidly spinning neutron stars that emit beams of electromagnetic radiation from their magnetic poles. If the beam sweeps across Earth, we observe regular pulses of light or radio waves. Magnetars. These neutron stars have the strongest known magnetic fields, capable of releasing enormous amounts of energy in the form of X-ray and gamma-ray bursts. X-ray binaries. When a neutron star is part of a binary system, it can accrete material from its companion star. This process heats the infalling material to millions of degrees, producing X-rays. Neutron star mergers. When two neutron stars orbit each other, they lose energy in the form of gravitational waves, causing their orbits to shrink. Eventually, they collide in a spectacular event called a kilonova. Gravitational waves. The collision generates ripples in space-time, which can be detected by instruments like LIGO and Virgo. Heavy elements formation. These mergers are one of the universe's primary sources of heavy elements like gold, platinum, and uranium. The debris from the merger is ejected into space, enriching the cosmos with these elements. Result. The merger typically results in either a more massive neutron star or, if the combined mass exceeds a critical limit, a black hole. Importance to the universe. Neutron stars play a crucial role in shaping the universe. Element formation. They are responsible for producing many of the heavy elements necessary for planets and life. Astrophysical laboratories. Neutron stars provide a natural laboratory for studying extreme states of matter and testing theories of general relativity and quantum mechanics. Galactic recycling. The material ejected during supernovae and neutron star mergers helps form new stars and planets, contributing to the ongoing cycle of stellar evolution. Neutron stars and humanity. Neutron stars indirectly contributed to the formation of Earth and life. Elements created in supernovae and kilonovae, such as carbon, oxygen, and gold, became part of the interstellar medium that formed our solar system. Unsolved mysteries. Despite decades of study, many questions remain. What happens in the core of a neutron star? The extreme densities and pressures push the limits of our understanding of nuclear physics. Are there other exotic states of matter inside neutron stars? Strange quarks, dark matter, or even entirely new particles could exist in their interiors. How do magnetars form and evolve? Their magnetic fields are far stronger than those of other neutron stars, and their origins are not fully understood. Conclusion. Neutron stars are cosmic powerhouses that bridge the extremes of physics, from the behavior of matter under intense gravity to the formation of the heaviest elements in the universe. They serve as a window into some of the most profound mysteries of the cosmos, reminding us of the interconnectedness of stellar death, rebirth, and the very matter that makes up our world. Don't forget to subscribe to our Digital Discoveries channel for more fascinating content like this. Like and share the video with your friends and family members to spread the knowledge and keep exploring the wonders of the universe together.